Big thumbs up.
Okay.
So whenever you guys wanna start,
I will.
you have to wait for the
Right, but I'm not in charge.
Right. Let's get started. All right, let's get started. Let me remind you of a few things in the coming days. On Thursday at 10, for those of you who are interested, we are organizing a small reading group on John Nichols' recent work. We have two papers that we're going to read, a recently published one on labels, labels of nature, and an older one, but a few years old, only on the role of tools in scientific progress, particularly in neuroscience. So we look at these two papers, going to be from 10 to noon here at the center. You're invited to come if you're interested. Also, John will have meeting on Thursday afternoon and Friday morning. So if you're interested in meeting John, please send an email to Shashi, and Shashi will schedule a meeting with you and John. On Friday, John will be giving at 6:30 p.m. John will be giving his ALS lecture on the 10th floor, followed by a reception, as usual. So next lunch and talk then is on Tuesday next week, but it's not in person, it's an online talk. You might remember we have a special series which we call featured former fellows, where we bring back people who have been fellows at the center to give us a lecture. And our next featured former fellow is Daniela Baxter, who was a postdoc here probably 3 years ago or something like that, just before COVID, to the field of biology. So if you want to come to this talk, you must register online and get an invitation to join the talk on Zoom. The registration link is on the center's website. So please have a look at the center's website. You can click on the calendar, you'll be on the page, and then you get an invitation to come to the next in-person lunch and talk then is on Friday next week. It's going to be given by David Wallace in 2 weeks from now, a week and a half. There is my great relationship, who was described to me recently as a Pittsburgh nobility.
Pittsburgh what?
Nobility. Which I didn't know.
I didn't know either.
Now you know. That's not the most interesting fact about Meghan, but she's connected to the French ice cream shop in Pittsburgh. Maybe that's an amazing privilege and admiration for Meghan. Exponential. But anyway, more seriously, Meghan Page is Associate Professor of Philosophy at Loyola University, Maryland. She received a PhD from the Department of Philosophy at Bob. Is that Bob and Mark? Bob and Mark, very good advisors. She's been doing a lot of work in the philosophy of science with focus on paleoclimatology and on general issues in the philosophy of science related to paleoclimatology, such as historical construction, the role of modeling and calibration in this area of science and more broadly in science. She also has done a lot of work in the philosophy of religion. And she is the leader of the Templeton-funded branch, which is called SCT Foundation. Is that the name?
Set, but yeah.
Set.
That's fine.
Set Foundation. Set stands for what?
Science Engaged Theology. But it's a play like Set Foundation. But it's the foundation for science. The worst joke is the one you have to explain. So
anyway,
thank you so much for that very kind introduction. All right, so today I'm going to talk about calibrating climate proxies and the proxy transform rules, which are rules made to be broken. So just to give an outline, I'm going to start by talking a little bit about measurement standards and the literature regarding measurement standards. Then I'm going to talk about calibrating climate proxies, I'll talk about what climate proxies are and what paleoclimatology is, and how you calibrate climate proxies. Then I'm going to raise the problem for the way that climate proxies are calibrated, basically, and talk about how even though this is like a procedure we go through, the end result is usually thrown out, which is why it's real maybe broken. And then I'm going to talk about ways that we recalibrate climate proxies. And then I'll get to the moral of the story and what I think this tells us about measurement and measurement standards. Okay. So the standard problem. So there's this very general problem of standards in philosophy, right? And it's always like, how can we evaluate any standard without some prior standard by which we judge it? It's the problem of norms. It's what's led us all down this road into this question of how do we evaluate things? What are the standards for judgment? Now, in the questions about measurement, more specifically, the measurement problem is how can we determine if some measuring device is accurate without testing it against some other accurate measuring device, right? So if you want to know if your thermometer, you're going to evaluate it against other thermometers. But how do you know that those thermometers are reliable? Well, you have to evaluate them against something else. How do you know that those are reliable? And it's kind of a regress problem, right? You got turtles all the way down. And that is sort of standard problem or the problem of measurement standards. So Chang famously attacks this problem in Inventing Temperature. It's a great book. I'll just assume everyone's read it because you're at Pitt, but if you haven't, you should read it. And just to kind of briefly summarize, he starts off with this quip, the scientific study of heat started with the invention of the thermometer, and goes through all of the sort of difficulties that people experience in the history of inventing the thermometer. And just very big picture summary focuses on, starts by focusing on finding the boiling point of water, right? So you have thermometers that can kind of gauge heat. You notice heat goes up and down. But to really calibrate them to like temperature where you get some sort of ordinal story, you need fixed points so that you can know that all of your thermometers are sort of measuring the same thing in the same way, right? That's how you calibrate them together. And so it turned out to be really hard to find fixed points. So first we had to settle on like, what do we think is a fixed point? Then it's like, oh, maybe the fixed point is going to be the temperature of water when it boils. But then it's like, what's boiling? A little bit of bubbles, a lot of bubbles. Then you get superheating. Then you get problems about the operationalization of the measurement. So it's like, how do we figure out the way that we're going to get the thermometer and the water to know that we're boiling, like that we're measuring it at the right boiling point, et cetera, right? And so Chang goes through these and sort of talks about how consensus is eventually reached by focusing on the temperature of steam rather than water. So it's a steaming point. And if you didn't dip your thermometer into the water, but just measure the steam right when it came off, you sort of got empirically the same temperatures. This worked empirically. It served as a kind of fixed point. It was a way of calibrating thermometers. Now there's also this addendum, which is eventually someone showed that even the steam point is not really fixed, right? Because it has to do with like dust particles. If you clean them out, you're going to get a different steam point if your air is pure. But it didn't matter because all of the air in all of the labs seemed to be like equally dusty. So that we could ignore it, and it was fine. This is the way that temperatures were calibrated. Okay. So now after this discussion, Chang points out, look, it's not a purely just empirical luck that this kind of calibration was reached. And it also had to do, it was sort of evolving in tandem with evolving scientific theory at the time, right? So prior to the development of thermometers, we already knew there was this really tight connection between the sort of temperature of water and saturated vapor and pressure, so that you could change the vapor pressure just by changing the temperature. There was this kind of single relation, and we knew that saturated vapor pressure is kind of equal to the temperature minus the change in space. So this is just like if you boil water to a point, you get the vapor, it'll fill up, it'll let off just enough vapor to give a certain pressure in your tube. if you raise the tube a little bit more, you'll get just enough more water turns into vapor to keep the pressure the same. If you want to change these quantities, you have to up the temperature. But so sort of theoretically, we knew there's this really tight connection between temperature and vapor pressure. And this allowed us to connect the sort of empirical discovery of the stability of the steam point with this background theory that what happens when water boils is it sort of gets to a pressure where it can overcome the pressure of the atmosphere. That's what allows the vapor to come out. That's what makes the bubbles, blah, blah, blah. So now we have a theoretical description and this kind of empirical fixed point to calibrate temperatures. Okay. So Chang's analysis. So Chang says, look, we can kind of trace the regress from thermometers, which have fixed points, to thermoscopes. Those are just thermometers that existed before you could put numbers to them. And those sort of just trace back to perception, right? We knew that these thermoscopes are working, that they're tracking heat because they went up when things felt hotter to us, and they went down when things felt cooler to us. And through that, he develops this kind of principle of respect, where you get various epistemic iterations, and through that, you build this ladder of constructive ascent that moves through all these epistemic iterations, helping us to have more stable, precise, and accurate measurements. Okay. So that's the big background. And then around tall, sort of the next epistemic iteration following this like idea of the relationship between theory and, well, maybe not the next, another epistemic iteration comes from around tall, which is the model-based account of measurement. And Tall defends this model-based account of measurement, which is similar to Chang's, but it's a little bit more developed. And the rough idea here is that every measuring device or procedure is going to correspond to a series of abstract or idealized models that kind of define the procedure. So whenever you're measuring a temperature, you have in the background, and this can be like various levels of worked out, a theory that kind of abstractly describes the process that you're engaging in too, right? That tells you something about the relationship between the thermometer and the substance, and what the thermometer is supposed to be doing in the substance, and what kind of information is supposed to be transmitted and how it's transmitted. That's all a background model that we have. And when we're working out a measurement, when we're trying to find a measurement standard, a fixed point or something, again, part of how this happens is whenever you get discrepancies, you're like measuring things, and you're sort of trying to get this stability where all of your thermometers are getting the same thing, or you're getting coherence between your measuring instruments. And it's sort of like a iterative process between adjusting your measuring process in the lab, like what you're doing, making that more effective, and adjusting your theory or your model, right? Recognizing that there's uncertainty where you didn't anticipate it, recognizing certain things in the context can like really change your results. So it's this two-strand process. Now this iterative process in the long run kind of produces standards, and I'll talk more about this a little bit, but those like, so you iterate until you sort of have this global coherence, and then you find some measuring device that is the most stable to which we can calibrate our other measuring devices, and that's kind of how we get measurement standards. So just a little bit more detail about the model-based account. So a lot of the questions in philosophy of measurement are going to focus on this relationship between what's called the measurement indicator, and that's just something like the dial on a gauge or the line on your temperature. That's your indicator, kind of the physical reading of the device, and the outcome. And the outcome of any reading is going to be the theoretical interpretation. So like when I say the temperature is 98 degrees, right? So your indicator is just the line on the thermometer. Measurement outcome is theoretical interpretation of that indicator. And like I said, Tall thinks this relationship is mediated by a series of models. So more specifically, measurement outcomes depend not only on the indications generated by a measuring system, but also on how the measuring system is modeled both theoretically and statistically. A model of a measuring system is an abstract and idealized representation of the apparatus, the objects being measured, and the elements in the environment, including in some cases human operators. So you have, like I said, you have this big idealized model through which you kind of theoretically understand your measuring process. Now, this model can also be pre-theoretic. So we talked about like Renault, who's doing these temperature experiments way before we had anything like calibrated ways of measuring temperature, but he had kind of two thermometers in the same substance. And you have these pre-theoretical assumptions that are helping you understand what's happening in your model, which is like, these are going to go up and down at the same time. Or like temperature is ordinal, right? That you can have hotter and cooler. These track this. So the model itself doesn't have to be fully, well, it doesn't have to be fully verified, which we'll get to later, but it's kind of just like your background picture of how the measurement process works. And sometimes these, like in the case of an atomic clock, these have become like really, really precise and clear and entrenched in very stable scientific theories. But it's not, that's not always the case. All right, so Tal uses this model to kind of think about calibration and explain the process of calibration in metrology. And that just is the sort of metrological answer to this question of, how do you know if a thermometer is reliable, right? And we say like, well, a thermometer is reliable, it's been calibrated. Okay, well, how does something get calibrated? So there's kind of these two methods of calibration. You have two different calibration functions that you're trying to work out in order to calibrate any measurement device. So the first is called or Tal calls it the forward calibration function. And that takes you from, it's like a function on some quality value to your indication. So in your measurement model, you're going to have some theory that's like, oh, you know, when the temperature is 98 degrees, the thermometer should look like this. And then you take some cases where you think it's 98 degrees and kind of see if you get that indicator on whatever you're trying to calibrate, right? That's the idea. And then you also have the backward calibration function, and that's where you try to understand relationships from indications to quantity values. So you represent, you know, temperature or whatever you want as a function of the indication, and you try to figure out what is this function that takes us from various states of our indicator to various states of the quantity that we're interested in. Now, even though he calls these the forward and backwards, in cases where you have a good model or you have some other measuring devices, you'll start with the forward calibration. But if you're kind of like working from the ground up, I think you often start with the backward calibration procedure, because you're trying to just get from kind of basic empirical knowledge to something a little bit more theoretically stable. But these are the two different calibration functions. Okay, and so he also makes this distinction between black box and kind of white box methods of calibration. So initially, when you're calibrating something, you just have this very direct sort of calibration function that you're trying to determine empirically, right? So we just say there's some relationship between temperature and this thermometer readings, and that's it. You don't think about all of the different influences that might affect this relationship. So you kind of ignore external influences on measurement. You'll have some measurement uncertainty, but a lot of times those measures are pretty large, unless you're working in a case where we just really know you're measuring tightly connected variables. And it's effective as long as you feel certain that you're only using your device in similar conditions, whatever that means. Now the next stage in calibration is white box modeling. And this is kind of where you start to pull that measurement process apart and unbox the relationship between indicator and outcome, right? And so if you're thinking of like caliper or something, you might have all of these different things that you know are affected. So depending on the atmospheric temperature, if you're measuring, like your materials might be more deformable. So you might get like slightly different measurements if they're a little bit warm, because they're going to respond to different things. So you can kind of pull, rather than just looking at the relationship between like your indicator and your outcome, you can look at all these mediating relationships, right? And this is kind of what we're thinking about in the model-based account, is what the model does is it unpacks all of these mediating relationships between your indicator and your outcome. And that helps you get better quantify uncertainty, you know, get more reliable results, know like what to screen off for in various experiments, et cetera, et cetera. Okay. So Tal uses this to kind of give a coherent picture about the role of measurement standards. So now measurement standards come into this view because we use, when we say like, when I was saying about the forward calibration function, and we want to know, we say like, oh, when it measures this block, it should get this output. How do you know that? Well, we usually use measurement standards to supply those reference values, right? So measurement standards are kind of what we can use in the input of any particular calibration function. So then it seems like, oh, what makes measurement standards special? Well, on Tall's view, it's just that these are more stable devices, right? It's kind of like, it's a pragmatic choice. So the issue is we want to make sure that everybody's watches are synced, but it's too much work to like have everybody say like, you know, try to calibrate their watches together at all of the different labs. So we pick some watch that we know is really reliable and everyone calibrates to that watch. And that's the standard. And then it's like, well, how did you get that standard? Again, we just go back down this iterative process, tracing back to kind of the idea of building up standards in chain. Okay. So one other thing I want to mention about measurement that I think will be relevant before we go on is that in my neck of the woods, which is stuff about like earth science and paleoclimatology, there's a lot of discussion about how weird can you get and still be a measurement, right? So because a lot of the like measurements in climate science are model outputs or like the outputs of like these really big complex processes that some people at Wired have suggested are not really empirical in the right sense. You get these worries about like, how weird can we get? How indirect can we get? And it's still a measurement. One, I'm actually not worried about that today, but I just want to put it out there because this is something that's in the background, I think, of what a lot of people are thinking about. So Wendy Parker has this great paper where she kind of distinguishes between like direct measurements. And that's where we think of something like a rain gauge, where it's like, well, the water goes in and you see the height, and that feels pretty direct because it's like 2 inches of rainfall is like 2 inches in the bucket or something. But it's not always that direct, right? You sometimes get a lot of derived measurements. So a different way of measuring rainfall is like a decibrometer, where you measure the size of the raindrops and how long they fell for and like try to work out rainfall that way. And you have to do a lot of calculations. And then Parker also makes the distinction, thinking about climate models, of what she calls complex measurements. And that's where it's like you're measuring something based on lots of different measurements that are being input into your model, and then your model gives another measurement. So you get layers of measurement. Okay, so I'm not going to say much about that, except that it's a thing, it's in the background of people's minds. When we talk about direct and indirect measurement, a lot of times people are thinking about this kind of measure of how close is our connection to the indicator, or how much, you know, computational trickery are you doing to get from your indicator to your outcome. All right, so that's background info about measurement. Now I want to talk quickly about calibrating climate proxies. Okay, so what are climate proxies? So the field that I'm really interested in is paleoclimatology, and paleoclimatology is mostly about reconstructing past, like climates of the past, which, you know, a long time ago just seemed like a fun thing to do so you could write cooler books about dinosaurs for kids, but now is really important because insofar as we want to understand climate patterns, a lot of the climate patterns that we study have sort of these long scale variability patterns, right? So it could be decadal variability, where you have a pattern that happens every 10 years. It could be centennial variability, where you want to find patterns that are happening over like 100 years. How can you detect those patterns? Well, you need a really long temperature record, right? To see a kind of pattern that happens like every 100 years or every 1,000 years or whatever in the climate. And we want to be able to detect this kind of natural variability in climate because that's how we can distinguish sort of contributions that humans are making to the climate from the natural variability. So it plays a really important role in the background of climate science. And another way that paleoclimatology plays a really important role is we can often find paleoclimate analogs of situations that we're in. So for example, the Permian mass extinction is considered to be caused by this major warming event where there was a lot of carbon dioxide. And so we sometimes try to reconstruct what climate processes happened in the Permian extinction to get a sense of how would a big influx of carbon really affect the system, the climate system that we live in. So that's paleoclimatology. So you're trying to reconstruct climates of the past, but you don't really have measurements of the past. At least not in the sense that we think about it, right? So we have a recorded temperature record for maybe like 150 years at best in some places, and even that is sparse, like, and sort of the kinds of instruments that we use to measure have changed over time, and that can cause various degrees of difficulty. So there's this real challenge, which is trying to construct a good temperature record for as long as we can, right? This is like a big scientific pursuit. We want the best quality climate reconstructions or temperature reconstructions that we can get. And we're interested in other climate variables too, but I'm just going to focus on temperature. All right. So and then climate proxies. So proxies are sort of what we use in lieu of what people would say are standard measurements. So proxies, well, almost. Okay. So the term proxy, you're probably familiar with in like other contexts. So a lot of times we'll talk about proxy measures and benchmarking. And here it's when you use something like the quality, you're trying to measure the quality of life in a city. So you use the gross domestic product instead because quality of life is like intractable, but we'll use the stand-in. So proxy variables are thought of as stand-ins. They stand in for variables of interest that we don't have any way to measure. In benchmarking, they're used to evaluate the effectiveness of policies. You also might be familiar with like proxy votes. So like if someone can't, like I'm the senator in my department, but like if I can't go to a meeting, someone has to be my proxy. They stand in and they vote for me. So these are these kind of standard uses of proxy. And in climate science, a proxy measurement is some preserved physical characteristic of the environment that can stand in for direct measurements. So we can't like measure the temperature, but we have stuff like ice cores, tree rings. So we think temperature like affects how wide tree rings get, something like that. And we can use these to extract information about temperature. So one example that I'm going to talk about today is foraminifera, which are just any kind, well, not any kind, but it's a lot of different kinds of shelled organisms that form shells in seawater. They're marine animals. And when they die, their shells fossilize. They go down to the bottom of the ocean and they stack up. And we can pull them out in sediment cores. And we take sediment cores from the bottom of the ocean. And they store, because their shells store chemical information about the composition of the water in which they were formed. And so we can use that to learn facts about like what was the seawater chemistry and also the temperature in a way that I'll talk about a little bit at the time when the shells were formed, and we have ways to date them. And so we can sort of use them to try to build this temperature record. And we do that through stable isotope analysis. So isotopes, if you're not familiar with them, are chemical atoms that have the same number of protons and electrons, but they'll differ in the number of neutrons. And so because they're the same kinds of chemical atoms, they have all the same chemical properties, but they have different physical properties. And they don't change over time, unlike decay. So sometimes we study isotopic decay. Those are isotopes that do change over time. Stable isotopes don't. And there's this background, the background picture of stable isotopes is there's just a fixed number of how many isotopes there are of different varieties for different chemical atoms. So that doesn't change. So like in the case of oxygen isotope analysis, which is what I'll talk about the most, O18 is like, there's tons of it. O16, there's not very much. And we don't think this changes because they're stable. So one never converts into the other. Now, so 16 is the one that's more common. But anyway, so O18 is heavier than O16, right? Because it has more neutrons. And so that means that it behaves a little bit differently. And we can use these physical differences that's how we're getting information about the climate. And a lot of it happens through del O18, which is called sometimes the fractionation record or the fractionation pattern. And really all that is looking at, in a bunch of different instances, changes in the ratio of heavy to light isotopes over time. So you kind of, in any sample, like in the shell of any particular forum, you can find out what was the ratio of heavy to light isotopes at that time. And then you can do this for a bunch of different shells and you see how that ratio varies over time. Now, we think that the variation in that ratio, and you can do it in these shells because they're made of calcium carbonate, so they've got oxygen. And the so the concentration is going to depend on the concentration in the seawater and the temperature of the formation. And really what's driving this is that lighter isotopes evaporate more quickly in warm water. And so when you have lots of heavy isotopes, you think that the water was warmer. And this is kind of the background mechanism through which we can extract information about temperature by looking at these variation and fractionation patterns throughout different shells in sediment cores. Okay, so and also the great thing about stable isotopes is like we think of their signal as being preserved for like in theory millions of years. They're not likely to degrade. All right, so this kind of pattern that I discussed is something we call a paleothermometer. It's the thermometer that we use to measure past temperature. And paleothermometers use proxy measurements like stable isotope ratios to determine their target parameters, like temperature. And they're governed by these things that are called proxy transform rules. And those are determined by calibration. So you can think of a target parameter as being expressed as a function of the proxy. And this is very much so actually I'm following like a textbook. In this section, I'm going to follow a textbook on how you determine proxies for foraminifera. And the first thing you do when you want to have your transform rule is you set your target parameter to be a function of your proxy. And this we know from Tal's stuff is like the backward calibration function. And then you get a statistical, you do kind of a statistical analysis of your calibration set. So there's no model. We don't have this kind of scientific theory that tells us about the relationship between fractionation pattern and temperatures, right? So what we do is it's like, well, we've got recorded temperature for 100 years. Let's look at the fractionation patterns here for the last 100 years and try to match them up to temperature, do some statistical analysis, and then we use that as our kind of proxy transform rules. And now we're going to project it back on for like 10,000 years or however deep our sediment core is. And we sort of measure for uncertainty then by like pulling out different points in our calibration set and testing them against the proxy transform rule. Okay, so we're doing to proxies something that's like black box calibration through this function. And then, as the textbook says, invariably the correlation between the target parameter and proxy variable is imperfect, and several more or less independent parameters will determine the behavior of the proxy. So in forums, so we know that the content, the isotopic content, is influenced by, like, for example, both temperature, but also the chemistry of the seawater at the time. And we just know empirically that seawater has different chemistry in different places. We again don't have full models that explain this, right? We sometimes have models of oceanic circulation which can explain changes in it. We don't have a rule to calculate like what would the chemistry of the seawater have been at that time. So we're working with like varieties of unknown variables, but you can add in correctives again through doing what are called modern calibrations, where you're just calibrating, you're choosing a calibration set that corresponds to the period for which you have measured temperatures, and you get these modern calibrations that you're trying to use as your rules to project onto your historical pattern. And so in the case now we get our forward calibration function, and that's where oxygen is a function of like temperature, ice, and a whole bunch of other stuff that I won't get into right now. All right. So then what's great is in this textbook, after it goes through this whole process of how you calibrate proxies, there's this quote, which I call the uh-oh quote. And it says, in practice, because most proxies are determined on biogenic calcite or represent the response of a biological association to the target parameter, natural variability has to be taken into account. It is therefore good practice to estimate the target parameter using more than one proxy. Only such a multi-proxy approach will lead to a sense of the confidence that can be placed in the reconstruction. The quality of the correlation within the calibration set is insufficient evidence for the quality of the transform back in time because the mixture of parameters influencing a proxy changes through time. Nevertheless, confidence limits derived from calibration sets are commonly offered as valid error estimates. Such limits are optimistic. All right, so what does this quote say? Basically, it's like, F that. Don't trust these rules. This is how we do it. This is how we can calibrate to modern temperatures for proxies, but we have reasons to be deeply suspicious of that. And the reason is we know that this relationship that we're modeling is actually not a stable relationship, right? It changes over time. So it's not a stable relationship in the context of interest to us, which is a very long time scale. So in different climates, you're going to get very different interactions between these variables and how they affect isotopic content. And there's lots of other worries about interference here, but that's the big idea. That's what I'll say for now. Okay. So now I want to talk about recalibrating proxies. So this quote leaves us at this place where it's like, yeah, we can calibrate, we can use proxies, and we have this method for calibration. It looks just like what we do when we're calibrating any kind of a measuring device, but also it's not reliable. What you really need is a multi-proxy approach. And you might wonder, like, Well, how do you make too good, like a good thermometer out of two bad thermometers, right? It's like, what's the point of doing a multi-proxy approach or testing proxies against each other if we don't think we have a reliable way of calibrating any individual proxy? And so I want to now talk about an example of one really successful intercalibration approach with proxies called the Patterson-Clark technique. All right, and this is like from back in the 70s. So again, I'm going to stick with stable isotope analysis and stick with oxygen isotopes because then we don't have to introduce any new stuff. But like you can study a very similar kind of fractionation pattern in ice cores. And here it's not just about warm seawater making the isotopes evaporate. It's about changes or alterations to the precipitation pattern that are caused by temperature. So it's like when it's warmer, you get more evaporation. And the lighter isotopes, they have an easier time evaporating. So you have seawater that's like denser with heavy isotopes. Also, whenever it rains, you get a lot of the heavier isotopes are released. And then all of that ends up as snow in the ice cores. And what's cool about glaciers is they store like every snow, right, that's happened in like individual kind of layers. And so what you can do with an ice core is you can sort of go back and analyze all of these different snowfalls and look at the fractionation pattern, which is the ratio of heavy to light isotopes throughout the different layers of the ice core. But of course, we have this problem, the same problem that we have with forums, which is one, I mean, the relationship that I'm describing between the fractionation pattern and like temperature affecting precipitation should make you feel a little woozy in your stomach, right? Like this does not feel like the temperature pressure connection that we saw in the case of first developing the thermometer. This is a very, like we do think, yes, temperature is going to drive a change in the fractionation pattern. But once again, it does not feel stable. It does not feel like we would have a really good way of screening it off from intervening causes. So there's something about it that feels a little eh. So how do you solve this problem? Well, one approach to solving it was to couple together the isotopic ratios with borehole measurements. Now, borehole measurements are like when you take the ice core out, you can measure the temperature at different depths. And here you can actually really reconstruct the temperature curve over time, relying mostly on just thermodynamics, which we think of as pretty stable. So you can get a pretty stable, like theoretically stable sense of what was the temperature curve. But what you can't figure out from borehole measurements is how quickly any of the increases or decreases happen, which was really important just like as an outside factor here, because what people were interested in was kind of like studying climate change or climate events, and we were trying to track back to like previous warming periods. And so we wanted to know like how fast does this happen and how big is the impact. You can't get anything like that from a borehole measurement. It's kind of like measuring like when you're cooking a turkey and you can measure it at different depths, and that's going to tell you something about how long it's been cooking and what the temperature was when you started. That's what you're doing in borehole measurements. And again, here we feel like these are reliable. They give us a temperature curve, but we have no way of getting a time index. Now that's to be contrasted with the ice core, right? Because there you get a really nice time index because you can kind of differentiate between different snowfalls through the layers of ice. But we have this problem of like we don't have a model that connects the fractionation pattern to the isotope record. And so, okay, so what do you do? Well, you couple them together. You basically say, let's, instead of trying to do these modern calibrations, let's assume the borehole measurements give us the temperature curve, and now let's fit the isotopic relationship to the curve, right? So you try to use the relationship between, use statistical analysis to get some kind of relationship between isotope and temperature that would predict this curve. And if you get a really tight fit, which they did in some of the Antarctic glaciers, then you feel like, oh wow, we've really tracked something here. So you're using these two things in sort of different ways. And that's how you get your temperature record. And then when they went back and like compared this to the modern calibrations and the kind of uncertainty measures, it was way more reliable. It seemed to be like doing a much better job at tracking the temperature signal over a lot of time. All right, so what's the analysis of this? Well, our background model suggests these two different sources kind of share a chronology of temperature, right? So why don't we worry about all of the things that we're worried about in the indicator outcome relationship when we're thinking about coupling together the borehole and the ice core record? Well, because we think they kind of, somewhere in them, they have the same temperature story, right? They were both in the same place. They were exposed to the same temperature. And instead of trying to isolate some stable relationship between an indicator and an outcome, which we don't think you can do because there isn't a stable relationship, or at least not one that we're close enough to understanding the structure of the world to be able to exploit, you look for this common story. You like try to pull out the common narrative that you think these local measurements are all going to have because they all experience the same temperature record. And if some weird climate events happen to one of them, it happened to the other one too. So you have a different way of like fixing your ceteris paribus, right? Because it's like they were all in the same place for the same times. They had the same experience. So you're not getting that relationship right. You're just trying to find a way to get them to harmonize on the experience they all share of temperature. Okay. And also, an interesting fact, the result's not generalizable. So you might get a really good way of predicting like a specific borehole from a specific, from that specific ice core, but you can't then say this is the general relationship between isotopes and temperature because it's going to be totally different somewhere else. Because what you've done is like just built in a lot of environment specific factors that you don't have to worry about because you were in the same environment. And also, even the technique isn't generalizable because if you go to the south where the glaciers have had melting, you're going to get too much mixing up in the layers of ice. So you can't get that really nice time index from the isotope fractionation pattern that you can get in like Antarctic glaciers. Okay. And also you have this problem, Elisa Bukulish talks about this, that whenever you intercalibrate, you lose the ability to like test two measurements against each other. So that's a different kind of problem. But here we think that the intercalibration, the fact that it works so well is supposed to give us confirmation in a different way. Okay, so that's it. So what's the moral of the story? I don't know. I have a lot of thoughts about this. I'm going to give them to you. I don't know if they're all the same thought. I don't know if they're different. I'm thinking maybe we can like upvote and downvote these in Q&A, and you can tell me where I should focus or what, if anything, you thought was interesting. But here's kind of what I take away from this. So 4 morals, I'll talk about them each briefly. So 1, not all measurement calibrations rely solely on the relationship between indicator and outcome. 2, proxies are distinct. Okay, so full disclosure, this paper was once upon a time a paper about like, why do we call proxies proxies? And then someone was like, no, this is an interesting point. So you should make it about measurement standards because people read that and only like 3 people read about proxies, which is true. But so there, I think that this gives us a way of like distinguishing proxies from other measurements, which is something about theoretical indirectness rather than empirical indirectness, something like correlation rather than causation. Now, 3, I think the indirectness of the proxy relations just suggests that they're very unstable. They're extremely sensitive to their particular context. And 4, I think that means that striving for this kind of global coherence that we've come to expect in the search for stable measurements is just a bad strategy here, and it might not be the best path to measurement accuracy. All right, so I'll go through these a little bit more one at a time. So yeah, as I said, a lot of the stuff in the measurement literature is focusing on how do we get a reliable relationship between indicator and outcome, or the indication and the outcome. And I just think that in historical science or narrative science, which is what I think of as paleoclimatology doing, these, like those kinds of relationships are only instrumentally interesting to us, right? Like what we really want is the story of what happened. And so sometimes like we care about if we can get some good kind of stable relationship to get a measurement, great. But if there's some other stable way of getting to the story, or like the chronology or whatever, that's our fundamental epistemic aim, right? And so it's okay to kind of use shortcuts, or this could open up really different strategies than just thinking of measurement as always iterating by proceeding towards some kind of stable standard, right? There's other ways to like get closer to the world than just getting more reliable relationships between indicator and outcome. So this is one thing that I think is interesting. Something else that I think is interesting. So there's this thing in paleoclimatology where you talk about proxies and it's like, what's a proxy? Well, it's an indirect measurement. And then philosophers of science are like, oh, measurement's indirect. Yes. that is true. But I think that there's actually two different sort of axes of indirectness that we need to be thinking about when we're thinking about measurement. And I actually think the one that we think about the most is empirical, what I'll call empirical indirectness. And that's what I'm taking as the indirect relationship between an indication and an outcome, right? So it's true that whenever you measure something, there's a gap. And it's like the weird philosophical gap between like the mercury and temperature, between the world and our theory. That's this empirical gap. It's always present in measurement. But there's a different kind of indirectness that I think we need to be paying attention to, and that's theoretical indirectness. And in the cases where our models, like the model of our measurement, is really telling us that we have reason to doubt the stability of some relationship we're trying to exploit, then that's got to switch up our measurement strategies, right? And so I think that's why scientists track proxy measurements as like a different kind of measurement. And again, I don't think this is the question of does it still count as a measurement or is it still empirical? I just think like, well, look, it's a distinctive kind of measurement. And what's distinctive about it is it's happening in a place where you have a lot of theoretical indirectness. And that gives you reason to mistrust the stability of any particular relationship you can kind of find in a data set, right? It gives you reason to doubt sort of the ability to make something global. Okay. And I think that's the relevant indirectness here. So 3, I think there's this point about global versus local coherence, which I should say something about because that was what was in the abstract. So I think built into our understanding of epistemic iterations is this idea that increased accuracy is going to be tied to something like stability or robustness. And this comes up a lot in Tal's account, comes up in Chang's account. But I think that really, like I said, our measurement models might tell us like, you're not going to find a stable relationship here. But there is a relationship that you can exploit in context-specific ways if you're willing to be smart and creative. And that's like an important thing to learn from a model and like an important way to conceptualize the way that measurement might iterate over time. I also think this kind of suggests that the connections between some of our measurement aims, like accuracy and stability, might be sort of accidental in the cases that we focused on. Again, so here, Elise Buklach also has a lot of work about like different kinds of things that you want in a model. But I think she's like, and it's like the difference between accuracy and stability. I think this is something a little bit different. And now, I think it's kind of an empirical question, whether or to what degree this instability will disappear in further iterations. So this goes back to the empirical versus theoretical directness. So the other thing I get a lot when I talk about proxies is people are like, oh yeah, well, proxies are messy, but that's just because we're in like the early iterations, right? Like, so when we get our worked out theory of the proxy, these problems will go away. Just like, this is just like what happened with temperature, but now we're in the situation. And I think we don't really know. I mean, I think we can't be sure that this relationship that we're trying to use is going to turn out to be a really stable relationship, or that we can get a really theoretically direct model of indicator and outcome here. That's an empirical question. We don't know how things are going to turn out. So I don't think you want to say like this is just early measurement problems. I think this is really something about just how we have to kind of fix our ceteris paribus in a different way. Okay, and finally, this is the end, and I'm also going to be like exactly on time. All right, so I'm now going to do what I'm saying you shouldn't do, which is make this very global point about this local phenomenon. But something I think this suggests is that maybe in the case of proxies more generally, it might be that we should focus on developing context-specific strategies for getting the signal that we want, rather than really stable strategies that can give us some kind of standard, just because of the nature of proxies and what they are. Now, context similarity can serve as a stabilizing feature in the absence of theoretical directness. So we don't have a theory that can give us a clear picture of what the relationship is between two things. Just putting them in as close to the same context as we can is like the best we can do. And again, it's never like, it's like, well, how do we know the relevant features of the context that need to be the same? You don't, but it's like, make all of them the same, or make as many as you can the same in whatever way that you understand. But the point is, this is like a different way of strategizing, because you're really focusing on like, when you look at local coherence, what you're trying to do is privilege context similarity over relationship similarity, right? And which again, I think makes sense in proxies. Now this generates other problems down the line, which is also in a different life what this talk was going to be about, is that second stage, because now you have to be able to like make different proxies talk to each other, and that can be really hard. So the upshot of when you try to like globally calibrate your measurement standard is it makes it really hard to compare results. Whereas if you really specify how you're going to measure in a local context, it makes it more difficult to compare results. And I think we privilege that standardization so that we can compare results. But I'm saying maybe there are cases where what we should be privileging is the context specificity, and then work on some interesting strategies for how to compare results. Okay, that's it.
I take a 3 or 4 minute break and then we come back.
Right, I'll see you down there. Oh my. No, she's not here. Yeah, of course. I want that transitioning. So we definitely have to have because I don't know if you got a chance to read the paper from which I gave the first part. Second part is about the way the liability tracks different differently with different kinds of phenomena, and that so it's very pathetic. I think to what you're doing. So let's do have lunch sometime. Yeah. I'm trying to get you. It's the presentation on out there. That's right now. So the brain's kind of elsewhere, but my brain's always here. So if you network, we're gonna do my network. You're gonna be friends. But if you have you found it fine. So no, okay, so I can send it to you. Just send a copy of it. I think the press keeps putting, can't get it to go away. Like a copy of it, you know, they make something fixed, but I can send you the earlier. And then let's talk about it. Because so I'm a coherentist too with it, but I include some other pieces of other than the ones you talk about. Oh, I also but not those. I was just trying to help. What are those? Yeah, no, I thought that was really quite interesting. Also another paper I will send you called instrumental perspectivism, which everybody migrated. That's how but it's interesting. It's using it rather than it's not really in order to look at this stuff. Right. So yeah, it's definitely like right. But it's very good. I gotta go. The time late.
Right, let's get started again. If you have a question, please raise your hands. Read the point.
Yeah, okay, so I have questions that are mostly clarification. So one is about this outcome indicator.
I should probably say an indication. I realized in my brain I would say.
Well, question actually about the other one, outcome. Like, why is it, so is it true that with outcome you basically mean temperature, for example? Or do you mean whatever temperature number we get to after our indicator points at something?
Like 97 degrees Celsius. No, Fahrenheit.
Yeah, but still, like, so suppose something that is not temperature influences your indicator to give something wrong. I don't know, it doesn't work. Then that would also influence whatever number, 94 degrees you
That's
have. So it would also influence the outcome. And that's what you mean by outcome. By outcome, you mean temperature influencing.
No, the outcome is just whatever theoretical interpretation you're going to give to the indicator. And sometimes it'll be problematic and then you'll have to go back. So like, let's say there's a case where I'm trying to take my kid's temperature to see if they go to school and it's like really low and I find out they just ate a popsicle or something.
Yeah.
The outcome is still the number that was assigned to it. But I just have now like reason to doubt that my measurement happened in standard conditions. So it's like, so that I might want to run the process again or something, but you still consider that the outcome.
Yeah. Okay. So that's makes sense because the word outcome. But then I'm not sure why you would look at, like, there's also the relation between whatever you want to measure, temperature, like the temperature of your child actually or something, and how that leads to your indicator. And is it true that that's a different relation and somehow the one between outcome and indication is more important? Or
Okay, good. I think I'm going to answer your question, but I might be missing something, so just come back if this is not it. But one is like when I'm talking about the relationship between indicator or indication and outcome, what I'm referring to in most cases is the theoretical relationship in the model. So we have modeled some kind of theoretical relationship in idealized circumstances between the indication and the outcome. And I think that a lot of times we think measurement is getting better insofar as we have like the best, most accurate model of what that process looks like in idealized conditions, right? So it might be that, when I first had a model of the measurement procedure, I didn't even consider like the ambient temperature of air affecting what I was measuring. But then I add that into the model. And so, but there's this other relationship, which is what you're talking about, which is like the actual empirical relationship between a particular indication and a particular outcome, right?
I think what I mean, but maybe is that like, I think something like temperature influences how your indicator gives something, and then how your indicator gives something influences how we get to a certain outcome. So it's a sort of different.
I think those are supposed to be the two calibration functions, right? Like it's like, because what you're doing when you're calibrating is trying to get those two relationships. So the forward, I think, is the relationship between the temperature and your indication, and then the backward is the relationship between the indication and the temperature. And the idea, like in the model-based account, is that we're getting more and more accurate measurements to the extent to which we can like precisify the models that describe that relationship theoretically. And it doesn't even have to be just theoretically. It might also describe something about the process, like where you put the thermometer, something like that. But yeah, so there's kind of the abstract, like the general relationship.
Yeah.
But you do the two different types of calibration.
Okay. Okay, I'm gonna try one more time. So suppose you have two rooms and one is warmer than the other, but something goes wrong with your measurements, and so the outcomes could be the other way around, right? Like, or is that not possible? The outcome is the temperature of the two rooms. I guess I'm just.
You would just think that your outcome was not reliable. So like outcome isn't a success term.
Yeah. Okay.
It's just the thing that you get. So you have your indicator, you put it through whatever you put it through to get. We have something that takes us from indicator to outcome, right? A lot of these get hidden in like a thermometer because it just gives you a digital reading. But like in other cases, we've got to work to get from point A to point B. And then whatever we get in point B is the measurement outcome. Now it might be wrong.
Okay. So
That's totally fine.
Any other question? Yeah, just go ahead.
Thanks a lot for your talk. really great. I'd like to know what you think about it. I mean, it goes a bit beyond with respect to what you were saying now. What do you think about self-calibrating computational models like deep neural networks and things like these, which arguably, I mean, function a bit differently from what you described here. But the thing the reason why I'm asking is that, for example, many biologists think that this model really, I mean, improve calibration significantly. So it even leads to less human involvement, which can be a good thing, since, I mean, some of these models were shown to be highly accurate, as accurate or even more accurate than experimental methods. But arguably, I mean, there's no human involvement in calibrations. The models rather do that themselves. It's like,
So, sorry, I feel like there's a couple of things that you're gonna be asking and I'm not totally sure what you're interested in. So like, one, there's this question that you might ask about like these really big complex models, which is like, are they still measuring, right? This is the whole, like, do they still have empirical content thing? So that takes us to like the Wendy Parker territory, right? Like where she talks about and I think this is on the whole spectrum of empirical directness, that question. You know, okay, how much calculation can we do where we think we're still doing a measurement or something like that? I don't know. I feel like to me, that's a pragmatic question of how we're going to use the term measurement. And I'm pretty flexible on it and would be open to different arguments in different domains of research for different reasons. But I don't have like this hard and fast rule about the term measurement. But is that what you're asking about? Because then I won't just talk about the other options. Okay.
Super, thank you. I have a couple of questions, if it's all right.
So you're good.
So the first one is really quick because what you talked about reminded me of what I read in the idealization literature. Michael Weiss book has this kind of a different kind of idealization called multiple model idealization, where you get like where you have idealizations and instead of just having one model of the target phenomena, you get like lots of models of the target phenomenon. All of them are deficient in some respect, but then you kind of create the model at the end, which is influenced by also you think that this kind of conciliatory approaches is much better. So that sounded a bit similar to maybe it's that, yeah. But my second question, more of a clarification question, is when you talked about the measurements, the example you had about the ice core and the borehole measurements. My question is there a kind of mutual interpretation going on, or do you interpret both the results of temperature and then see what's going on, or do you mutually interpret the measurements and that's your final answer?
I think it's a mutual interpretation. So I think with the borehole, you do get something which is like the general curve of the temperature, but you can't index it according to time. So it's like, you know, like this went up this much, but did that happen over like, well, one, it's hard to, there's a whole different question with indexing these to like temperature standards we have, but just with the time issue, it's like, okay, did that happen over 100-year period or 1,000-year period? You have no way of knowing that from the borehole measurements because that just isn't in the signal that they give us. So you are doing some interpretation of the borehole signal because you're kind of putting a time index on it that you're getting from the fractionation pattern in the ice core. Now, similarly, the fractionation pattern in the ice core, because we just know that these isotopes are influenced by the temperature record, but we don't know what that relationship is, or we don't have a model of it, you can't really parse out the full temperature curve. And so that's what you're getting from the borehole stuff. So it is this kind of mutual interpretation.
Right, yeah. So it's kind of, it's quite different from taking, say, I have two pieces of evidence. I know these two pieces of evidence are maybe systematically or have their own kind of default defeaters. So I kind of interpret the evidence and then I see, oh, okay, this can't be right, this can't be right. This is my whatever I have to conclude. But you're saying no, there are these two kind of uninterpreted pieces of evidence. I take a joint interpretation of both of them and then I get the stuff. But then the question would be, how, I mean, because this is, I don't know how joint interpretations work, but that doesn't seem a kind of trivial job, right? Because interpretations you usually think are kind of data to world relations or something like that. And having a joint interpretation is not a trivial matter even for these simplistic models, you have to do some stuff, so.
Right. I mean, I think like the stuff that you have to do is statistical analysis. Well, like I think first you have to like get these two different data sets, then you do this kind of, then you have to create a measurement model kind of by Tal's idea. And the measurement, like what happens in our measurement model here is we think like, and this is what I was trying to talk about with the sort of common cause picture. But so we have this background theory that tells us, look, the ice core and the borehole were in the same place at the same time, and the temperature they would have both had the same experience of temperature. So somehow there's this harmonized story that we want to get at. And so what are we trying to do? We're trying to see like, what is that signal? Now we've got some clues from our background theory of knowledge of how to do this. But what I think is interesting about these kinds of joint interpretations, and part of like what I'm trying to get at in this talk, is they're so situation specific. And really involve this kind of scientific creativity, because you're not just getting a kind of theoretical amalgamation of two different results, right? You're kind of like taking what you know and coming up with a way to throw them together and thinking if we can get this kind of fit, it would give us this kind of confirmation. And sometimes you do. And then it's like, oh, we learned something good today. And sometimes you don't. But like, it's just a very different way of trying to iterate and perfect your measurements to get a more accurate read on the world than I think is what's usually captured in the measurement literature.
Sure. Thanks again. So my question, I think, is kind of part checking my understanding of some of your morals and then asking you to kind of like
I have no
reflect a little bit further on it. So if I'm understanding correctly, you want to sort of traditional measurement literature on this stuff focuses a lot on this relationship between indicator and outcome. And to the extent that there's models discussed in that literature, there are somehow models that like explain what's happening or model what's happening between indicator and outcome. And you're wanting to shift our attention to like, in part, these sort of local relationships between different indicators, which of the same outcome. Is that okay so far?
Well, so I would say I don't want to say that the model, I actually think that the model-based account of measurement is supposed to go beyond just your indication and your outcome, right? Because it can tell a story about how you get the indication. Like that could be, because you might know that like certain devices are really prone to human error or something like that. And that would be part of your model. Like people are bad at reading these or doing something like that. Like that stuff's gonna get built in because you measure the whole process. But then it's like, what's the significance of the indication outcome relationship comes in this question of how do measurements get better, right? Like how do they iterate towards the kinds of things we want? And it's like, when we have a stable relationship here, that's how they're getting better. But I'm saying like, well, I don't know. Sometimes
you don't have a stable relationship. You need two different indicators and then. So I think my question is about what's going on with two indicators there. So you said something like, models might direct us to this creative search for local coherence between different indicators. So in this case, it would be like the borehole measurement and why am I blanking on the other thing? The isotopes. Yeah, thank you. Right. So we're looking for coherence between these, but I wondered, like, is that really a modeling situation, right? At some point you use the phrase like background model, tells us that these things are measuring, they have a shared chronology. But I'm wondering if the theory that like things that were in the same place at the same time should be measuring the same temperature, like, is that really a model? Or are you departing from basically the question is like, how far are you departing from the model-based literature?
He says, I mean, this is what I was talking about, like in the model-based account, he says that you can take a model to include pre-theoretic assumptions.
Okay.
And so I'm thinking of those as kind of pre-theoretic assumptions.
Okay.
I think that sometimes I think with the model talk, I think sometimes the model talk is really useful because again, in like certain measurement situations, like the atomic clock situation, there are these really good mathematical models, you know what I mean? Like whatever. But Tal wants us to be a general account. And I think the nice thing about model language as opposed to theory language, is a lot of time you have to use like a bunch of different theories or your background assumptions are not all stemming from like one theoretical context. And so model language is loose enough to give us a way to integrate those in our background picture.
Sure. I wondered if there was something specific to historical situations here though, right? That the model language doesn't capture as much. You said something about like a shared story or something like that at some point. Right, like place and time and like these things are like parts of, or traces of the same process or something like that, right? Like,
Yeah.
that seems important here. I don't know. I mean, I'm just playing with things out loud here, just wondering if like,
Me too.
to what extent is this, you know, is there something cool here that we can do specifically in historical cases, which would show us like, hey, we're, you know, the model picture is not just, is like missing something that, you know, is a resource we have in historical cases where we have to look for, you know, pieces of the puzzle of the same story or something. I'm not sure, but
Yeah.
this is me reflecting.
I mean, I do think that there's a lot of, well, attributes. Like on the one hand, I think like, yeah, there's a lot of the specifics. That's why I kind of try to introduce also like, just like, what are we doing in paleoclimatology? Because I think the fact that what we want is like that our, like, I think our end goal is really shape how our scientific research
Yeah.
program is going to
Yeah.
proceed here, because I think it's like, we're trying to get this story, and we're in other cases in measuring devices, I think we're trying to get a way to like synchronize the trains.
Sure.
And that's a
Yeah.
really different thing to want to do. And you're gonna want to like privilege different aspects of your process, whatever. So yeah, I think that stuff matters. But I also think, so I've actually talked to Ron a bit about this, and because he's been thinking about it too in the case of proxies in like psychometric stuff. And the shared thing I think here is that in a lot of like the big data-driven AI analysis of what we think of our proxy measures in like psychology, you're getting really bad, and often really bad in the sense that they're like very racist or very classist results, because because like they're so context sensitive. Right. And so I really think there is something here about theoretical indirectness and context sensitivity that just extends to the nature of proxies in different disciplines.
Yes.
Insofar as we have to be more careful about assuming or striving for the stability of an indication outcome.
Thank you.
So hello. Yeah, quick question about, I'm just trying to understand what's puzzling about the case. So that's, so let me see whether I understand the case well, and then tell me exactly what's really surprising about the case. So on the one hand, we do some measurement and we get a description of the changes in temperature, but they're not indexed to time, because they're not timed. We just know that there was some changes, but we don't know how, we don't know when they took place, and we don't know how long they took place. That's one representation of what happened. It's incomplete, obviously. On the other hand, we use iScore, and we get some other information, right? So we get some information about when changes in temperature happen, but we don't know exactly how much it changes, what temperature changed, right? So we got another representation of what happened in the world. Now, and then we put the two together because they provide complementary information about what's in the world. And of course, we can use one to provide the information that's missing for the other, right? Because now we have a time series about when the changes happen, we just don't know the magnitude of the changes. Then we can use that to benchmark the other one with respect to time. That's what you're thinking about, right? I'm not mischaracterizing.
No, that's right.
What's puzzling about that?
Nothing. It's great. It was a
No,
super.
it's kind of, I'm just wondering why. I'm just wondering why this is. You know, you've got two representations of the world. They're not about the same thing. They're complementary. You know, so you've got two maps of the world. You know, you can have a map that measures distance, a map that measures altitude, and when you put them together, you have more complete maps of the world. I'm just not grasping why there's an epistemic problem here. Why there's even an so like, what's puzzling about the case that I mean, I'm just not on it. I mean,
So,
maybe
yeah.
there's nothing really puzzling, but
Yeah, I don't know. So there's a sense in which I'm like, yeah, it's not supposed to be puzzling. It's supposed to be like a creative solution to a problem.
yeah,
right?
no, that's
what I think
true.
it is. So I think it's a creative solution to a problem. And I think that it's not puzzling because we can make sense of what they're doing.
Yeah.
But I think that when we see this as the solution to the problem, it proceeds in a very different direction than we're predicting solutions to these problems will proceed. Right?
Based
So-
on Tal's view, right?
based on Tal's view and even Chang's view, and kind of these ideas that like what we're looking for is more global coherence, and that's how we get more confidence. So I think it's like there's this kind of presumption in a lot of measurement literature that we build confidence in our measurements and we perfect our measurements through robustness and stability. And here you have,
I'm gonna follow up with that.
Okay, but like, so in this case, you just don't get that. There's nothing stable about this. You couldn't do it. I mean, there's lots of glaciers where you couldn't even run the same procedure. And the specific relationship that you get isn't gonna work, but we think that it's really reliable. And I think, and so like, that's what I'm trying to get at. I mean, that's the puzzling thing. It's not, the actual case is not supposed to be puzzling, it's supposed to be brilliant.
No, that's helpful. Yes, thanks. So I have a quick follow-up about the stability of my original question. I do worry, but I'm not sure. I'm hesitating about whether there's not an ambiguity in what stability means. So stability on one side is context insensitive.
Yeah.
So a result is stable if you do it, if you get the same result across different contexts. That's one sense, and maybe that's a sense that does not fit your case. Because it's a different glacier, then you're going to get different relation. But of course, there's another sense of stability that fits your case. Is if you were to redo in the same context, the same thing, you would still get the same outcome. So you hold the context fixed, and then now, in psychology, it would be called reliability, right? Or maybe you repeat a measurement in the same context, but maybe not reliability. Forget about it. Just repeat a measurement.
Yeah, that's right.
So now, that's in that sense, stability is a feature of your case, right? So, and now I wonder whether you
theoretically,
okay,
right?
but,
Not empirically. I mean, but that's part of the problem.
But so you agree that it's two different senses.
Oh yeah.
Now I wonder whether you person to people you're criticizing are more concerned with stability as context insensitivity or stability as repeatability within the same context.
So they say it's robustness is stability across multiple contexts, though not
like measurement across different
Yeah.
group impurities.
They talk about both,
Yeah.
but like the idea is that both are goals. And but the repeatability, even the repeatable. So I wouldn't separate them in quite. So yes, I get what you're saying. The repeatability thing is a little bit tricky
No, I agree.
because then you have to say like, well, what makes it the same
I
context?
totally
And that's exactly what I'm saying collapses in this case, because it's like you can't have the same context that is not exactly the same experiment. So you can't run the same experiment in the exact same context in the relevant sense. I mean, we could do the like statistical analysis again. I mean, we could go back and like brush up on our, like, you could reanalyze, like, you might be like, oh, we got the wrong measure of the isotopes, right? You could go back and think like our indicator was wrong, but you couldn't really do, I guess you could pull it, like right next to it. Yeah, you could. And they do, but then again, it's like, I feel like what you're doing here is trying to just make that context as stable as possible. Yeah. But and again, I think that like there's, well, it's also it's tricky though, because it's like if you pull another isochore right next to it, it feels sometimes like you're just running the same experiment. Like you're not getting enough variability to feel like you're getting some kind of stable even in the same way. Because I'm assuming that like what you're saying is like, look, it's one thing to say that my thermometer keeps getting the same result when I measure something the same temperature. And it's a different thing to say that like a bunch of different thermometers get the same result when they measure my boiling pot or something like that, right?
Yeah, there's many ways of buying,
Yeah.
one might say,
Yeah. I think that's right. So I will say that like specifically, Tal talks about you want robustness across different contexts. But I think that even talking about stability, on the one sense, I think it's just hard here to like specify what we need in context or what a repeated experiment would be.
Yeah, related to this, couldn't you say that one way of dealing with context specificities is because you are looking at a common cause? So in this case, you have two different things and they share the temperature pattern of climate heating. But to the extent that you can assume that whatever basically other confounders for one measurement are independent of the ones for the other measurements, then whatever they share sort of no longer is influenced by these unique things, confounders. So
because it confounds both of them? Is that the...
No, because it don't confound both of them. So if you have to, that's why I would think you look at two different proxies.
Ah, good.
Because if you have some things that affect one proxy, then you could make a model for that proxy and that changes over time. So you have no idea. You have the same for the other proxy, but because they both share temperature, but they are influenced by other stuff. Whatever they share is not influenced by these specificities of the one and not by the specificities of the other. And in a way, you could see that as making it a bit less context sensitive, because you take away all of these specificities and have it only influenced by temperature.
Yeah, I mean, it's tricky though, because I think like what you're saying is true in a token sense and not in a tape sense. Because so it's like, I think that like, it's like, yeah, we have this actual causal event that happened, right? Like, and like that causal event is stored in both of these things. And so we can like ignore these different things because we're focusing on what's the same.
Yeah.
But we couldn't like model that. Do you know what I mean? We couldn't like whatever we figure out in that case for how we pinpoint that signal, we can't now go use in a different case, which is what we think of a lot of times when we like make the procedure more stable.
Yeah.
So it's like, it is, that's what I mean when I say it's like not contact. It's like, yeah, it is an event and that event is stored in, it's like a very particular
I
relation.
agree. So you cannot translate that model to another context, but you do sort of account for context specific factors that you don't want in your measurement still.
Yeah, I think that's like the glory of this thing, is that you find a way of doing that without going through all this work you could never do of like getting this really stable relationship between these. Yeah, no, I think that's-
So there is some, it seems like there is some context sensitivity that you take care of or something, but just in a different way than that you can then apply it to other contexts.
That's right. It's like, I do think that there's a sense where you're focusing on it's like you're able to assume a certain kind of stability by being really local.
It's very similar to how we have different measures in psychometrics. So suppose we were interested in measuring extroversion, and we think, oh, in some way someone being extroverted is manifested in going to a lot of parties, and it's also manifested in someone being talkative. Then there might be very different things going around in whether someone goes to parties. It might be influenced by all sorts of factors, like, oh, if my mom is sick, I cannot go to a party, and it's all context specific. But then as soon as you look at only the things that are shared among all of the things that we see as extroversion, then these things no longer count or something. So I guess that's sort of also,
it's more stable.
even though this whole extroversion model, I don't believe in it, but still, that's the sort of the rationale for why you look at something shared. So I think that works nicely here as well. I was wondering, so you had the O quote, and there you also mentioned that one solution actually in the textbook was already looking at multiple proxies, right? So isn't that
Looking at what? Multiple proxies?
yeah. So isn't that already getting at the same idea?
No, I think it is the same idea. What I was trying to say is like, well, why should we trust a multi-proxy approach? And then I was just trying to elaborate. So the next part I was just trying to elaborate is like, what does the multi-proxy approach look like? It's not just like getting the temperature here.
Right. Okay.
So that was, that's right.
Yeah.
No, I meant that to be confused.
Yeah. Okay.
No? Yes, we're going to do now. Getting more and more useful, sadly. So, thank you very much. All right, thank you, guys.
I think I had a similar question. Which is if I
Oh, that was recorded. For TikTok.
channel,
Channel.
not necessarily like real temperature, then don't you have to worry about like a third?
Oh, I took that.
Yeah.
Yeah.
Okay.
Why? Yeah.